Thank you very much, Sergey. Thank you for inviting me. Great to be here. So what I would like to talk about today is a sort of overview of some of the remarkable phenomena that we have observed in deep learning recently, and well, not so recently as the case may be, and in particular, how interpolation sheds light on some of this phenomena and where sort of it leads us, both theoretically and to some extent practically as well. So what I am going to be talking about is primarily based on this kind of review paper that I wrote recently, which appeared in Acton America last year. So, well, as we know, deep learning has been a great success in the last 10 years or so. And one thing which we have observed is that, it's based on very complex structures. Oh, and by the way, I should say, please do feel free to interrupt me with any questions, and I will try to also monitor chat. But feel free to interrupt me. I'm more than happy to slow down and answer anything that you may.
I'll monitor the chat for you. So if there are any questions in the classroom or in the chat, I'll just basically ping you.
Thank you. So we have this rather complex structures, things like this, and there are lots and lots of parameters, and there are also lots and lots of hyperparameters and training parameters in different various aspects of this mathematical objects, which make them quite non-transparent, quite difficult to understand. So we have something which works well, but not something that we understand well. And I think recently we have started to gain some understanding of the phenomena of these objects and the associated phenomena. And what I should point out is that a lot of our understanding really, not even maybe so much an understanding of deep learning as such, but actually understanding of phenomena of machine learning more generally, things which we sort of knew before. You'll see some quotes, for example, from Leo Breiman, but also sort of didn't know. So it's a little bit puzzling. So things which were observed, but yet somehow not fully digested or fully accepted. Okay, so let's sort of see what the issue is, and it's kind of you can say that this this idea that this very complex neural network performed so well precipitated the crisis of machine learning theory. I mean, on one hand side, there was the very nice talk in 2017 by Ali Rahimi and Ben Recht, and they basically argued that machine learning has become alchemy. In the following sense, alchemy is kind of a pre-scientific chemistry. So you have a kind of pre-scientific point of view that you do certain manipulations and sometimes they're successful, but you don't have a sort of rigorous view on what makes them successful and what not. So you tune some parameters, you play with the things, you get results, but it is not clear what makes those results. There is no somehow overarching theory for this. A kind of counterpoint to that is that point by Jan LeCun, who said that machine learning theory is looking for lost keys on the lamppost because that's where the light is. So there is a cartoon of a drunk looking for the lost keys under the light. Of course, there is no reason to think that the lost keys were actually lost under that lamppost. So from that point of view, right, we have a theory, but the theory is explaining something else, and it's not really useful for understanding machine learning. Of course, in general, there is no reason that a theory has to be like a lamppost, that it has to be attached to this. You know, a source of light needs to be attached. So hopefully we can sort of detach it and use it to eliminate various phenomena that we have. So now, you know, there have been recognition of these issues, and Jan LeCun, of course, that the deep learning breaks up basic rules of statistics. Much before that, Leo Breiman, a prominent statistician from Berkeley, who used to be at Berkeley, he actually wrote in 1995 this nice notes, reflections after referring papers for NIPS. And he basically was asking the following question: why don't heavily parameterized neural network overfit the data? What is the effective number of parameters? Why doesn't backpropagation head for a poor local minimum? And so on. So there had been this understanding that something was a little bit off for quite a while. And so here are some of the here are two of the key questions that have been puzzling. And the first question is a generalization, and why do neural networks have so many parameters and so complex, but they seem to generalize to unseen data quite well and do not seem to, you know, suffer from overfitting, at least not too much. And the second question is optimization, and why can non-convex objective functions be optimized? And arguably, we understand the second question now quite well. I will concentrate primarily on the first one. And that one we have some understanding now, but it's still far from complete, in my view. So now to the prism, and why is interpolation is a prism? Well, what does a prism do? The prism takes light and it splits the white light. White light, of course, is a mixture of different frequencies, and it splits it into its individual components, into individual frequencies, as illustrated in this picture. So it takes something which is complex, like the white light, and it makes it a sum of something which is simple, like individual frequencies. So in some sense, I think interpolation plays the same role in machine learning, is that it takes complex, very complex setup, and it splits it into kind of this individual phenomena, which are easier to understand, and I'll discuss what this means. So basically, the idea is that you want to allow analysis by separating a complex phenomenon into something much simpler, where these individual components can be analyzed separately. So let's now get down to it, and let's first see. So the plan is, first I will discuss a sort of classical approach, you can call it Vapnik's approach to the problem of generalization, and then I'll point out what was the crisis of machine learning, kind of our modern interpretation of it. Why doesn't it explain what it should be explaining? So what do we have? Well, in machine learning, as usual, we have data, xi, yi, and we can think about a simple classification problem. Xi data points in RD, for example, images, you know, cats and dogs, and yi is, you know, label, -1 for cat and 1 for dog. And the goal of machine learning in general is, given this data, to construct a function from the space of images to R, well, specifically -1 and 1 in this case, that best generalizes to new data. Well, now what does generalization mean in this case? If you sort of think about standard statistical assumption, and I'm sort of assuming it is somewhat familiar, you would like to, you assume that xi and yi are sampled from some probability distribution, and I would like to find a function which minimizes the expected value of the loss. For classification, for example, it can be just what's called classification or binary loss. Like every time you make a mistake, you pay 1. So that's basically how this works. Yeah, and please do interrupt and ask questions. It's really worth it, I think, to slow down once in a while and discuss sort of in more detail. Okay, so now, so that's the goal. Now, how do algorithms work? So typical algorithms work by something called empirical risk minimization. And actually, a better term would be to call it algorithmic empirical risk minimization. Because basically you construct a loss function over the training data, and then you have some algorithm, which is usually gradient descent type of, well, stochastic gradient descent type of method, to minimize the empirical loss. And this of course, is called the empirical loss. Empirical means that it's taking over the training data. So you run this gradient descent, you find something which minimizes the empirical loss, and then you hope that this will give you a good prediction in the future. So notice the difference. The goal of machine learning is to find this F star. The goal of your optimization procedure is to find this F star ARM, okay? And the sort of first key question here, of course, is the choice of H. And what is H? This is the class of functions of hypotheses from which you choose your functions. For example, it can be an architecture of a neural network, right? An architecture of a neural network is a hypothesis space because you're training to find a neural network with a certain number of neurons, for example, or certain number of layers and so on. Notice that for this problem, there is no class of functions. You just want to find F, which minimizes the loss. But when you're minimizing over the training data, you have to choose an architecture in advance, because if you don't have an architecture, you could just choose any function which fits your data. And obviously, many of these functions are useless. There are infinitely many, right? They cannot all be good. And of course, they're not. So key question here is the choice of H. And classically, we have a kind of a very simple picture, this U-shaped generalization curve. And how does this U-shaped generalization curve work? So if your H has low complexity, so what does it mean, low complexity? It means that your H has few functions, for example, only linear functions, maybe. Then your training sample is not fit too well because you don't have enough complexity to fit your training data. And your test sample, of course, is also not predicted very well. So you have what's called underfitting. Now, if my model complexity is very high, then I can fit the training data, but I'm kind of fitting the spurious correlation, which only exists in the training data, but don't really generalize. So my test prediction is not good, the generalization is not good, but my training loss is close to 0. And therefore, it stands to reason that the optimal is somewhere in the middle. So that's basically what it is. This is a classical view, of course. I'm showing it to show that it's not quite the case, and we will see what happens. So kind of on the left of this, you have overfitting. Underfitting. On the right, you have overfitting. And the goal is to find the sweet spot where the model complexity is just right, kind of Goldilocks. So that's basically how you choose H. So you choose H somehow in the middle, not too complex, not too simple. Now, what is the sort of mathematical setup for this? Mathematically, you can say that you can do the following, and this is the ERM theory of learning. So remember that the goal of machine learning is to find this F star, but the goal of empirical risk minimization is to find this F star ARM. So this is a result of optimization, and this is the best future prediction. So if you look at it from this point of view, then you just need to say that somehow F star ARM is sufficiently close to F star, right? Because that's really what you want. That, by the way, is always true, right? Because whenever you use F star ARM, if F star ARM is not close to F star, you are not going to do well. Now, the question is how to connect these two quantities. And the Vapnik theory has a very nice recipe for this. In what he says is that the theory of induction is based on the uniform laws of large numbers. And two, effective methods of inference must include capacity control. So let me first describe uniform law of large numbers. And second, I'll talk about capacity control. So first, what is uniform law of large numbers? Well, uniform law of large numbers. So what is the law of large numbers, right? The law of large numbers is something like that. If I toss a fair coin a bunch of times, on average, I'm going to get 1/2, right? That's the law of large numbers. So expected value and the empirical average are close enough. And uniform law of large numbers is basically the same thing holds for any f in my function class. So, of course, I don't have a coin here, but I have something very similar, right? I'm sampling this trading data, and I'm saying that for any function f in my hypothesis class, the expected loss is close to the empirical loss. The empirical loss is what I actually observe when I toss the coin, and the expected loss is the expectation of them. So if the things are approximately equal, they satisfy uniform law of large numbers. Now, what about capacity control? So capacity control basically just says that the F star can be approximated by something which is in this class H. So there has to be something in the class H which approximates F star, because if you don't have anything which is good in my hypothesis class, then it is hopeless, right? I'm not going to do it. So here is how it works. It sort of boils down to this, what you may call this Fezzik bound. What you see is what you get. And so the usual way this works, the usual way this bound is written is something like this. So on the left, you have what you see. I'm sorry, on the left, you have what you get, which is the future performance of your predictor, right? The expected loss. On the right, you had what you see, which is the empirical loss, right? The empirical loss is what you observe in trade, plus some term which relates to the capacity of your predictor. And classically, in Vapnik theory, this is VC dimension. So it's something like square root of C of n, when C is a VC dimension of your class. If you're not familiar with it, it's okay. It's not really important what it is. And n is the number of data points. So that's basically how it works. And there are lots and lots of different bounds of this form, probably, you know, hundreds. With VC dimension, fat shattering, Rademacher, covering numbers, and lots of other things. So now, how does this work? Sort of all together, and you can think of the following picture, which is a nice figure from the Vapnik's book on statistical learning theory. On the x-axis here, you have hypothesis space, and as you're increasing the hypothesis space from left to right, right, you're taking bigger and bigger hypothesis space, what is happening here? The empirical risk is going down because you have more and more models to fit your data, your training data, and what is called the confidence interval is going up because the C is increasing. So that term corresponding to square root of C over n becomes bigger. So one term goes down, the other term goes up. And because the bound is composed of both, you get this U-shaped curve. And the optimum is at the bottom of the U. So this is a kind of more mathematical explanation for that curve with bias variance trade-off curve that we saw before. So this is the picture. And one thing that you may notice actually is that that something a little bit peculiar happened there, is that the C doesn't depend on the data before, right? The C is just associated to the class itself. But clearly, that's a little bit strange, right? Because if you take so suppose I want to use linear functions to make my prediction, right? I kind of know a prior that most of the linear functions that I have are useless, right? Because if I have like, if I have red points and I have blue points and I want to separate them, taking a random linear function is going to do very poorly. It's just basically going to do as well as a, random predictor. So I'm only interested in those functions which already do at least reasonably well. And most of the space of functions doesn't sort of come into play at all. So why do we need uniform law of large numbers? Why do we need a bound for everything? It would probably make more sense to only have a bound over things which are already at least somewhat useful or potentially useful. So indeed, that can be done. And that was the idea for the so-called margin bounds and other a posteriori bounds. You can make the C to be data dependent, and in particular to depend on the margin. I'm not going to describe it much more. But the sort of underlying structure of the WYSIWYG bounds still is the same. You have what you get on the left, what you see on the right, and this kind of capacity term, whether it's data dependent or not. Okay, so now finally, we get to interpolation. And what is interpolation? Interpolation is simply, I would say that the function interpolates is f of xi is equal to yi. So it's kind of a classical, so if you're familiar with classical fitting, right, this is just exact fit. Now, if you have interpolation, it seems that this type of bound is a little bit problematic. Because why? Well, if f of xi equals to yi, right, then my training loss is equal to 0. But my test loss generally is not expected to be 0. So you get a pretty peculiar, kind of thing. On the left-hand side, you have non-zero. On the right-hand side, you 0 plus some sort of complexity term. But as we will discuss later, this complexity term or capacity term is not really that helpful. It doesn't seem to be that helpful. So traditional view is that interpolation basically is bad because it overfits. So if you think about this graph from this, yellow Springer book, they say that the estimate on the right seems more reasonable than the estimate on the left, which interpolate the data, because somehow interpolating the data is bad, right? You just overfit. And the same thing is essentially said in the Elements of Statistical Learning, another well-known book. It says that, however, a model with 0 training error is overfit and will typically generalize poorly. So in a sense, interpolation is just dismissed. It basically says, well, look, it's overfit. And that's a sort of traditional view of overfit. However, the situation is actually not so simple. It's a little more complicated. And there is a nice table from Understanding Deep Learning Requires Rethinking Generalization by Zhang et al. And they ran a neural network on CFAR10, which is an image data set, and they trained it to have accuracy 100%. So you would think this is probably pretty severe overfitting, right, given this previous claims. However, what we observe is that the test accuracy is not bad at all. It's almost 90%. So there may be some overfitting, hard to say, but it's certainly not very significant. So somehow training to accuracy 100% is okay. And indeed, this was actually not something new. And if you're familiar with boosting, and that was the method introduced in the 90s. And one observation that people made is that experiments with boosting, the test error of the generated hypothesis usually does not increase as its size becomes very large, and often is observed to decrease even after the training error reaches 0. So it's quite surprising. So you basically can drive the error to 0 with the accuracy to 100%, just like above. And then, well, you still have good generalization, right? Your test error continues to improve. So essentially, this is the same thing as what we observe with deep learning. And yeah, as we've seen, it was known in some settings for at least 20 years. So what's going on? Well, first, let me point out that this is suggestive, but does not directly invalidate what you see is what you get bound. And let me give you a sort of more specific experiment, which makes this point, I think, much more clear. And the key idea here is to add label noise. So suppose I start with clean data, right? I have some red points, I have some blue points, and you know, I just assume that the optimal predictor is something like this, right? You can think of it as a mixture of two Gaussians. The red points come from one Gaussian and blue points come from another Gaussian, so that the overlap is small between those Gaussians. Now what I'm going to do, I'm going to add label noise. What do I mean by label noise? I'm just going to randomly flip some percentage of the points. So I flip this two blue points on the left and this red point on the right. Right? So now it's kind of the data have become noisy. So now if you think about it, the optimal predictor is still the same line, because as long as I'm flipping this labels at random, the fact that they're flipped doesn't change anything. I should still predict the same way as before. But that, of course, is no longer an interpolating predictor. So notice on the left, this predictor is interpolating, right? It's perfect. Everything to the right of this line is blue. Everything to the left is red. Now this predictor is not perfect. It's not interpolating. And if you think what an interpolating predictor would look like, it would look actually very, very complex. It would be something like this, right? Like this will all be blue and the rest would be red, because you have to somehow account for all the flipped points. And that looks like a terrible idea, right? So what I would expect that the model complexity needed to fit the data grows dramatically when I flip some of these points, but the optimal predictor, the base optimal, doesn't change. So I should see very bad overfitting. So that's, you know, if I'm in this traditional point of view. But let's see what actually happens. And I think this is a kind of important diagram. So let me explain what this is. Yeah, so let's not worry about this curve, just concentrate on the green one and the red one. So I think this is a key experiment, the key experiment. So what's on the x-axis here? On the x-axis is the amount of label noise. And this is, by the way, for a MNIST, subset of a MNIST, I think 10,000 points from a MNIST. So this is a 10 class problem, predicting handwritten digits. And the amount of label noise is what percentage of my data are randomized. So for example, if it's 10%, then I'm taking 10% of the training set and 10% of the test set, and I randomize them to have a random label. So I just choose a label between 0 and 9 at random. And you can see here that the green line is actually the best possible. Why is that? Because, well, if I'm randomizing 40% of the labels, I cannot do much better than 40%. Actually, I'll do slightly better than 40% because sometimes when I randomize, I just accidentally give it the right label. But I cannot do much better than 40%. The same thing with 60%, I cannot do much better than 60% for classification error and so on. Of course, when I randomize 100%, I am here because I'm going to make 90% of mistakes, right? Out of 10, I just accidentally do 10% of the time correctly, everything else is wrong. So the green line is the best possible predictor. Now let's look at the red line. Well, the red line is Laplace kernel machine, but it doesn't really matter what it is. You get similar results with neural networks. The important thing here is that it is trained to have 0 square loss. And 0 by 0, I mean it literally something like 10 to the minus 25 or 10 to the minus 26. It's machine 0. So it's as overfit as possible. And it's possible for a kernel machine to do that because you can think of training a kernel machine as matrix inversion. And matrix inversion, of course, is something which is quite nice to do in a computer. You can do it quite accurately. So here is a remarkable thing. I'm fitting, for example, like if you look here, right? I'm fitting my data. 60% of the data that I'm fitting is pure noise, right? So should be terrible overfitting because I'm just fitting all this noisy data exactly. But what I'm observing is that, yes, I'm doing, of course, slightly worse than the best theoretically possible, this green one, but not much worse at all, maybe 3, 4, 5%. So even though I'm like fitting this noise like crazy, I'm actually only overfitting very mildly, if at all, right? I'm essentially tracking the green optimal predictor. And even at 80%, it's still quite good, right? Maybe 10% worse or something. There may be some overfitting, but it's pretty minor given the amount of noise that I have. I mean, certainly you would expect that noise is a bad thing in general, right? The more noise you have, the harder your problem is. So you really see that there is not much overfitting, even when you fit very, very noisy data. Okay, any questions about this? This is kind of a key point here, is that it really shows that this idea of overfitting doesn't really quite hold water in practical experiments. You can have exact interpolation up to numerical accuracy, and you're still doing just fine. Questions, comments?
So on your classification error, wouldn't like a random classifier get to an accuracy of 50%? Why do we have the classification error as 40%?
Sahir, would you mind repeating because I couldn't quite hear it.
Misha, the question is like, why don't you get like classification error of 50%?
Random classifier.
Random classifier.
Correct 50% time.
I think it's an
Why? Sorry, somehow the sound is a little weak.
Yeah, Misha, the question was like, why a random classifier won't, achieve like 50% error. I think the confusion was that the student think it's a binary classification, but it's it's an MNIST. If I understand, it's an MNIST experiment, right? So you have 10 classes. So the random predictor will basically achieve like a 10%.
Yeah, right. Yeah, thanks for clarifying this. Yeah, so this is a 10-class problem, right? So if you just predict at random, you will have 90% error, 10% accuracy.
Any other
You
questions?
can of course do the same problem, the same exact experiment with binary, but then you would be at 50%.
Yeah, I have one question, Misha, myself. So these few samples that the model makes errors compared to like optimal base, do they have any particular statistical property? Are they like samples that are more difficult than the other samples to classify or not?
I think it is true. So we have not done, this was an experiment in that ICML paper. We did not look at that, but I think other people have showed that it is true that there is some sort of systematic, they're somehow harder to classify. You can kind of even select noisy points by looking which ones are harder to classify. So I think, yes, I think they do have certain statistical properties.
There are two more questions. Yes, go ahead.
So about the interpolation thing, when we are working with such high dimensional data like CFAR or MNIST, the data is living in a 32 by 32 space, for example, are we calling it interpolation? Is the model actually doing interpolation, or should we think about extrapolation?
So if I understand the question, I'll just repeat the question. The question is for experiments run like on MNIST or CFAR, so is the model actually doing the interpolation and basically what it interpolates to?
So on CFAR, those experiments, it's not quite, so this experiment, I think it's not exactly, so it depends what you call interpolation. It has 100% accuracy, but it doesn't necessarily interpolate in the L2 sense, in the square loss. So it's interpolation for accuracy. The ones in this, I think that's kind of nice about this particular graph, is that it actually interpolates. It's this classical notion of interpolation. You fit the data exactly. It's not just a sign of the data.
Great. So there's one more question. Yes, please.
Explanation for why the difference phase optimal is greatest at the middle, and then it tapers off at the bump shape.
Yes. So the question is like the difference between the red and green curves, basically the empirical and the base optimal. So why does it grow? And basically at the end, basically they match because it's a random prediction. But basically the question is, why does the gap between red and green curve grows versus the noise label?
Right. Well, you would expect it to grow, right? Because the green curve is optimal. So it doesn't care that the data are noisy, right? It does the best possible. But the red one gets more and more corrupted by the noisy data, right? So you would expect, in fact, if you had really bad overfitting, you would expect something like this, right? You would expect that curve to go like sharply up because it's fitting noise. But it's growing, but it's growing very badly. Of course, you would expect it to grow because also think about this, as I'm increasing the amount of noise, there is less and less useful data there. So I should do worse and worse, right? Even if I somehow magically can only select non-noisy data, I still have less of it. just because more and more data are corrupted. So it's very natural, I think, that it has to grow.
Makes sense. We have two questions from Zoom participants. Misha, if there's time, so we can get these questions. Otherwise, we can basically get these questions later.
Maybe I should continue and we can ask more questions later, if that's all right.
Yes, very good.
Thanks everyone for questions. Yeah, so in any case, what's the problem now with the bound? I think from this point of view, it becomes very clear because, well, let's think about this high noise level, right? Like at 80% or something like this. Remember that my empirical loss is equal to 0. So if I want to get anything non-trivial at all, it better be that this capacity bound, the capacity term, is less than 0.9, right? Because if it's bigger than 0.9, I can just as well say, okay, it's 0.9, it's random. So everything bigger than 0.9 is useless, but it's better be bigger than 0.7, because if it's smaller than 0.7, it's wrong, because I know that the best possible predictor is at 0.7. So you can kind of think about it this way. To be correct, it has to be bigger than 0.7. To be useful, it has to be smaller than 0.9. And now there are a bunch of issues here because the constant needs to be exact, right? Even if I'm off by a factor of 2, I'm kind of dead here. And conceptually, you know, like how would it know about the base risk? So yeah, it doesn't, it's sort of hard to imagine how it could possibly work. And indeed, there have been work showing Nagarajan and Colt in particular, and Bartlett and Long, showing that at least in certain settings, there are no bounds of this form which work. Now, here is a kind of the same thing, but presented in a more realistic, I think, setup, kind of like what happens in neural networks. And here is what is happening here. I'm training the same model at the same kernel machine, and I'm just training it like a neural network, you know, epoch to epoch. So on the x-axis, I have epochs. And here is the interesting thing. So what I'm observing, if my epochs are, you know, increasing, the SGD trade error goes down. Then it goes down after 20 epochs to something like 10 to the minus 5. And what you can see that the test error is also decreasing. It's going down. But here is the interesting thing. The interesting thing, even if I complete the trading, what do I mean by completing the trading? I drive the error all the way down to 0. So this is interpolation, and I can drive it by 10 to the minus 27. This is not done by SGD. This is done by direct matrix inversion. You cannot get that far by SGD. But you can drive it to 10 to the minus 27, and you get essentially 0 for the trading error. But what's remarkable is that you get, for the test error, you get basically the same thing as what you get after 20 epochs. So going from fit of 10 to the minus 5 to 10 to the minus 27 really makes essentially no difference for the tester. So interpolation is okay, right? I can drive the error to 0 and it's okay. So that's kind of an upshot. And I really like this quote from Ruslan's tutorial. He basically said that the best way to solve the problem is you want to make sure you hit 0 trading error. And this is not the end of it because you can tune parameters and so on. But if you just hit the 0 trading error with your neural network, you already get something which is pretty decent. So arguably interpolation, if not exactly best practice for deep learning, but something quite close to interpolation is the best practice. Now, let me actually, I'll get back to this. What we have seen is that people are building these bigger and bigger models, and that has been a major sort of thrust of recent machine learning. And what you see is that like each circle here is the number of parameters in these different models, and it just has been growing. This is to scale. So you now have models with hundreds of billions or even trillions parameters. So you do like expand these models, and I'll discuss why expanding the number of parameters may be something which is good. So here is a kind of the puzzle of generalization, and the interpolation doesn't appear to overfit, contrary to statistical and machine learning beliefs. Yet the practice of deep learning is arguably closer to interpolation than to classical settings. So the new theory of induction, to borrow from optic, cannot be based on uniform laws of large numbers with capacity control. So how can interpolation generalize? And let me discuss maybe something which is very simple and very suggestive, which is this one nearest neighbor predictor, or one nearest neighbor classifier. And if you think about it, what is one nearest neighbor? One nearest neighbor, so if I have a bunch of data points, right, this my trading set, given a new point, I simply select the point in my trading set which is closest to this new point, right? And this is known as a prototype method, one nearest neighbor predictor, one nearest neighbor rule. And this is clearly an interpolating predictor, right? Because if you think about it, it becomes clear that the empirical risk of this predictor is 0. And in fact, there is a classical analysis of it showing that in the limit, one nearest neighbor has twice the base risk. Actually, it's bounded by twice the base risk, meaning that it's only twice as bad as the optimal predictor. And this is really not predicted by empirical risk minimization. So you can actually do better, and I don't have time to describe this, but there are some really interesting kind of schemes when you can do better than one nearest neighbor. And maybe you sort of, let's ignore this, but let's just look at the picture. I think this picture is very nice. It explains what's going on. So what do I have here? I have this little circles are my data points, and they're sample from y equals x linear plus Gaussian noise. So y is equal x plus Gaussian noise. So now, of course, the true model generating the data is simply y equals x. So if I don't have, if I sort of a priori know what my data are, right, I should just predict y equals x. So that's the best prediction. You cannot beat it because I know the model. Now, if you use one of these kind of interpolating schemes, it turns out that you get something like this red curve. Now, this red curve is a little bit crazy, right, because it spikes at every data point. And notice that no data point is actually close, or very few data points are close to the blue line. The blue line, of course, being the optimal model. So at every data point, you're away because there is noise. So here is a remarkable thing. Even though this red curve looks crazy, and it's not close to the blue line at any of the data points, it is on average still optimal. So you can prove that this is optimal. This is an optimal predictor. And that's one thing. And the other thing is not only that, but actually, arguably, deep learning does something similar to this. And in fact, surprisingly enough, this can be proved, at least in some certain settings for very deep neural networks. But I won't go there today. But that's basically how you can establish a connection showing that deep learning like literally does something like that, at least in some settings. So that's basically what interpolation does. It's crazy, but it can be mathematically proved to work. Now, one curious corollary of this is kind of interesting. It relates to this adversarial examples, right? And adversarial examples, things like this, right? You take an image, it's a dog, you add some invisible noise, like changing a few pixels perhaps, and you get an ostrich. Well, you don't, of course, get an ostrich, but your neural network interprets it as an ostrich. Now, if you have label noise, you can kind of prove that this actually has to happen under interpolation. So if you're interpolating, then you necessarily would have adversarial example whenever you have label noise. Now, this is not to say that it's a full explanation of why adversarial examples happen. There are somehow alternative explanations and different mechanisms, but at least it is nice to see that what you get from interpolation is actually very consistent with the phenomena that you observe. Okay, so oh, there is something is messed up here. Sorry. Oh, what happened? Sorry, if you can just give me 1 second. I think somehow some slides are. Oh, I see. I think some slides got hidden somehow. Is this okay? Can you see?
Yes.
Okay, so let me now describe this kind of idea of what happens in actual neural network and parametric model, and this idea of double descent. And I will describe the double descent for. Well, maybe I'll start with this example. And here is a really simple example. This is just a one hidden layer neural network with ReLU activation. So you can view it as the random ReLU features because the first layer is fixed and I'm only training the second layer. And I have here some data points, right? These little circles. And if I use a neural network with 3 neurons, I have something like this picture, which seems like a pretty good parametric fit. Now, if I increase the number of parameters, then with 30 neurons, I have this kind of fairly crazy curve. And this seems like classical overfitting, right? I'm just kind of going back and forth, up and down. And now if I am, so you think, okay, this is overfitting. But something really interesting happens when the number of parameters goes even further. You have 3,000 neurons and you have this very nice non-parametric curve going through, a smooth curve going through my data. And let me just skip this. And this is kind of the idea of the double descent risk curve. So what is happening is the following. First, you have this classical risk curve on the left. And when you're increasing complexity, you sort of go from underfitting to the sweet spot, which is the bottom of the U, to overfitting. But then you realize you can increase complexity even further. And in the overparameterized setting, you hit the interpolation threshold, right? So your empirical loss drops down to 0 once you have enough parameters. And beyond that, surprisingly enough, like sort of traditionally, you would expect, okay, things are bad. But what you actually observe in this modern, quote unquote, interpolating regime, more parameters actually helps. And the more parameters you have, usually the better you are. It's not always true, but it's very typical. And so there are two key points here that you may think about it. Is that the classical curve ends at the interpolation threshold, essentially where modern machine learning starts, and that very complex models can outperform classical models. So this is what is happening, and you can actually ask, like, so this has been shown for a bunch of different setups, and you can ask the question of like, well, but how is this? What is this phenomenon like? Like, what is this? Is this really something which happens universally? And the answer is, at least for linear regression, you can show that this is, in fact, a universal phenomenon, and that in the following sense, it's kind of precise. And there is a very nice paper by Holzmuller, ICLR 2021. And he showed that double descent is essentially inevitable whenever you interpolate. And let me explain maybe this setting, and then I'll discuss sort of an extension of this. And then I'll probably should finish in a few minutes. So what do I have here? So suppose I have y is equal wx, so it's a linear model, plus eta. So eta here is noise. Oops, oh, why is it not working? Oh, not sure I cannot draw. Oh, it doesn't work. Okay, in any case, eta here is noise. And I am going to minimize the square loss. So I'm assuming that my square loss is equal to 0. It's an interpolating model. Then what they showed in that paper is that the loss, the excess loss of my predictor is bounded from below by sigma squared n divided by p plus 1 minus n, when p here is the number of parameters. So let's think what happens. How many parameters do I need to fit my data? Well, I expect if I have n data points, right, I need n parameters. So if p is equal to n, in the denominator here, p and n cancel out, right, and I simply get the excess loss is bigger than n. So I have this peak. The peak is of the size n, right, the number of data points, times the amount of noise. But now suppose p is increasing with respect to n. So the bigger p is, the smaller the excess loss needs to be. And if p is much larger than n, then I can show that I can, at least in principle, do arbitrarily well. So the upshot of this is, for interpolating model to do well, you have to be way, way to the right of the interpolation threshold. It's really, so you cannot do well close to the peak. You have to be way to the right. Now, what happens? Well, in practice, people don't actually run this to interpolation, typically, this neural networks. You just train it, and you train it to have the empirical loss to be small, but typically not 0. And the remarkable thing is that the same thing happens, and this is actually joint work with Nikhil Ghosh, very recent, from just a month ago, is that something very similar happens whenever we train below the loss level. And let's not worry too much what exactly it means below the noise level, but basically, even when my loss is not 0, right, I don't fully interpolate, even I just interpolate something to like 1/2 of sigma squared, the same thing holds. So what I have is that the excess loss, so how well I do compared to the best possible, is bounded from below by sigma squared n over p times something, which is, you can think of the 1 minus tau to the 1/3 to the fourth power. Don't worry about it. Think about it as 1/2. So essentially, the same thing happens. So whenever you train to have empirical loss much smaller than the test loss, you have the same phenomena that you need to be significantly over-parameterized to do well. So that's basically a kind of upshot that this is not even a phenomenon of interpolation itself. It's at least for linear system. For non-linear, it's less clear what is happening. But yeah. So maybe I should finish here. So let me maybe summarize and say one word about optimization. So here is the landscape of generalization. So here is what we observe. So on the left, you have this classical, landscape with a U-shaped curve, and classical, what you see is what you get bounds apply. And on the right, you have this modern interpolation regime. And when I say interpolation, it seems that even when by interpolation, you don't even have to drive the error to zero. You just need to drive the error to be low enough, and you already have the same thing, which is exactly what people do in practice, right? According to the Ruslan's quote, right? That's where you start. You drive the error to zero or close to zero. And now we're starting to have some analysis. There have been a bunch of papers in recent 2-3 years, in primarily still for linear case, but now some for neural networks as well, that we can prove that these interpolated predictors are actually optimal or close to optimal. And one interesting upshot of this is that overfitting, we can view it differently now, that overfitting is not directly related to your training loss. It's actually a kind of a range of parameters in the parameter space. So if you're overfitting, you can add regularization, and you can reduce the number of parameters to cope with overfitting and kind of try to find the bottom of the U. Or to the contrary, and this is the modern way, to increase the number of parameters in your system. And it has essentially the same effect. Okay, so let me maybe say one word about optimization, since I really didn't have time to say anything about this. But so the key question is, why is SGD so successful at optimizing highly nonlinear neural network? And let me just say that traditional view is that tractable optimization is somehow equivalent to local convexity. And you get something, a picture like this, which has a bunch of local minima. Of course, it's not really possible to separate local minimum and a global minimum. Now, what we have in practice is actually something quite different. And I think maybe one picture to have in mind is this sort of valley landscape, when there are many global minima, and the set of global minima is this kind of curved valley at the bottom of the landscape. And it is easy to see that such a landscape cannot be convex, but yet gradient method, in this case, can find a global minimum. So maybe I'll stop at this point, and I'm happy to take any questions.
Thank you so much, Misha. Let's thank okay, so we have some time for questions. Yes.
So for the model complexity, are we using the number of parameters in the double descent phenomena, number of parameters as a proxy for the model complexity? If that's the case, do we know if when we're increasing the number of parameters, the effective dimensionality also increasing? If that's not the case, then is the number of parameters could be a good proxy? I mean, it could be the case that the model has a lot of parameters, but the effective dimensionality.
Yes, so I'll repeat the question. So Misha, the question is about the x-axis in the double descent. So the question is if the number of parameters is used to basically represent the model complexity, and would that always be the case that if we increase the number of parameters, the model complexity will increase. Yeah.
Yeah, so in this case, so I think this is kind of an illustration of this. Yeah, so the number of parameters increases. It's a little hard to know what to make of model complexity in general. I mean, the number of parameters is something that you can measure very easily. What is model complexity? Well, it really depends how you measure it, right? Model complexity at initialization, or model complexity at training, and so on. I prefer to think about the number of parameters just because it's a much cleaner way to think about this. And it's not so clear what the right, how do you measure complexity correctly? It's not really at all clear. So I think it's still an open problem, very much so, like what the right measure of model complexity. However, what we do know is that if we want to have good results, the number of parameters has to be large, at least for linear models. I mean, for nonlinear models, it's likely to be the same thing.
So there's another question. Yes, please go ahead.
Mhm.
So if zero training loss is not a problem, then why bother with early stopping and things like that? What about the training process informs you when you stop early?
So I'll repeat the question. Basically, the question is why do we do early stopping in training if basically the 0-1 loss, if we just like let it run, it will lead to a good solution.
Oh yeah, so early stopping is generally a great idea. So let me show you this one again, right? So what happens with early stopping here, right? I can stop it at basically at about 20 epochs, right? And the result is essentially the same as letting it run to infinity, right? To 10 to the minus, to get there 10 to the minus 27. So early stopping is a great idea because you're saving, you don't really need like exact interpolation to get good results. And it's running it beyond 20 epochs would be just a waste of your resources computationally. And sometimes it even gets worse if you run it. So early stopping is a great procedure because I don't think it has that much effect as a regularization procedure, but it has tremendous effect as a kind of computation saving sort of technique. And in practice, especially, so here I had a way of actually solving the problem exactly because it's a kernel machine, but with neural network, usually you cannot do this.
Very well. I think there is a question from a Zoom audience, Sangwei. If you want to unmute yourself and ask your question.
Yes, thank you. I actually have two questions. The first is about the slides you showed where there's Bayes, optimal Bayes and a Laplace kernel. In that slides, you show that neural net is actually worse than the Laplace kernel and more similar to the Gaussian kernel. So I would expect the neural net is more similar to Laplace kernel than the Gaussian kernel because, yeah, could you explain, is there anything missing from these slides?
Yeah, that was the result we got. I think it's I don't remember which neural net is. Yes, I would expect in general that it would be kind of similar. If you use like a ReLU neural network, it should be similar to the Laplace kernel. And that's what we observe in many cases, but here it's a little worse, similar to Gauss kernel.
I see.
I don't remember which activation function we took there. So I don't remember the exact neural network.
Okay,
it's in the paper.
I see. So another question I have is about the role played by the data in the over parameterization theory. So I think the reason those large models really work is not only because they are over parameterized, but also they see a lot of data. So I wonder if there's any study on the role of the data in this region.
Yeah. So definitely data, of course, is very important. And clearly, like one one big improvement has been that now we can take these models and train them with, like billions of data points. What we have seen, however, that at least for this one, let me just go back to the bound. So if you look at the bound like this, you do see that n over p should be small. So so at least ideally, right, I want p, the number of parameters, to be significantly bigger than the number of data points. So when I have a lot of data, ideally, I want to take neural network, which is even significantly bigger, like have p at least like 100 times the number of data points. In practice, of course, it becomes a little bit tricky for various reasons, because also, like some of the neural network, especially the very huge one, right, they're trained on so much data that they're not even reused. It's like essentially a single epoch. So it's a little hard. But yeah, I mean, ideally, we want P to be bigger than N.
See, thank you.
Fantastic. So I'll ask the last question. So great talk, and I think we have seen like amazing benefits of overparameterization in generalization and also like solving non-convex optimization. But as you mentioned, there's also like a downside to it, right? In terms of potentially adversarial examples or other distributional shifts in the data. So how do you think about like such trade-offs? So because at some point we need to, in order to like have reliable models, we also want the model predictions to be, pretty robust against like such small perturbations in the input. And overparameterization may hurt those measures. So I wanna hear your thoughts on these trade-offs.
Yeah, I feel it's not really so. It's not so much of a parameterization as such. I feel that whenever we basically train below the noise level, so whenever the training loss is low, right, we will have this type of stability. So it seems that this is the kind of price we pay for this benefits of overparameterization, right? Overparameterization, okay, I didn't really discuss it, but it's kind of nice to optimize, and it does seem to be pretty good for generalization and so on. But whenever we train, so I think this kind of, whenever we train below the noise level, we're essentially in this mode where we have to pay by probably some sort of instability there. So I don't know, I don't have a very sort of, I don't have a very good intuition about the nature of this trade-off. Okay, maybe you have a better understanding of this, but it does seem to be to some degree unavoidable, right? Because how do you deal with this? Well, you can add some regularization and make it more robust, but you usually pay for that, right? And maybe if you know the manifold of the data, you could do better and so on. So it's it seems like a somehow quite subtle trade-off.
Yes, certainly. Okay, thank you so much, Misha. Really enjoyed the talk. So let's thank the speaker one more time.
Thank you very much.
Okay, thanks.
Bye, everyone.
Bye.